Hey, look at this. Looks like a bit of a mess. Looks pretty complicated, but it actually isn't. I want you to glance around the screen, have a look at each of these, and see what you think. What do they all have in common? What do you reckon? They're all integrals, but what is the integrand? The thing here that we're integrating, what do they have in common? Okay, can you see it? Okay, and what are we doing? We're trying to integrate any possible function we come across, find the area under the curve and all that sort of stuff. So this is the next level, isn't it? Let's come down, and did you get it right? They're all composite functions. They're all fogs, if you like, a function operated on the result from another function. And here's the common function that they're all composites of. The linear function ax plus b. Because if we apply f of x where f of x is x to the n to this function, we will have ax plus b to the n, won't we? That'll be our fog, our f operated on g. And if our function was e to the x, that would become e not to the x, but operating on the result of g. It would be that. And if we had our function 1 on x, it would become 1 on ax plus b. Do you get it? It's a nice cross-link here with composite functions and fog and goff from earlier. So let's do it for sine, and that would become the sine of ax plus b. So can we actually integrate these functions, these composite functions? What is the integral of ax plus b to the n, where x is a variable with respect to x? Well, come on down and let's see if we can work it out. Okay, so coming down here now, here are a few screen clippings here from Hayes Publications, using their textbook here for the minute. And let's have a look. They reckon the integral of ax plus b to the n with respect to x is 1 on a, increase the power by 1 divided by the new power plus c. Can you see it? I think they're right. We've got to do the two parts of the function separately. We're going to do f first of all. Increase the power by 1, divide by a new power, and then instead of multiplying by the derivative of our inside function, the g function, we're going to divide by it. Let's check it out over here. What would be the derivative of 1 on a, ax plus b to the n plus 1? We're going to go backwards and check it out now. So if we did that, derivative here be, now 1 on a stays out the front as a constant, and then we're going to multiply by ax plus b. Now what do we do with ax plus b to the n plus 1? It's m plus 1 ax plus b to the 1 less power, and the other n plus 1 was already there. Okay, and then we must multiply by the derivative of what's inside of the bracket, isn't it? It's a chain rule or function rule for a linear case. So actually it does work out. Okay, when we differentiate that, we have to use the x to the n rule and then multiply by the derivative of what's in there. That's the chain rule, isn't it? We get a chain of derivatives here. Okay, so working backwards, we do have to divide by the derivative of our g function, our function in here. It's a composite function approach. Let's do the next one. The integral of e to the ax plus b. The integral of e is itself. Okay. And then, though, if we think about differentiating that, would be timesing by a. So now we have to divide by a, and we don't forget the c on the end. That's always a mark. Very important idea. Let's do that one over here then. It's a derivative of e to the ax plus b plus c. Should have done that above as well. Derivative of a constant is 0. Then it's going to be 1 on a, that's just a constant. Derivative of e is itself, but we must multiply by the derivative of the function up here. It's a composite function, so that will cancel, and yes, it does work. It's true for each of them, isn't it? This division by a here is reversal of the composite function derivative rule, where we would times by the derivative of that function in there. Okay, so just remembering, we better do this one down here. D by dx of neg 1 on a cos ax plus b plus c. Okay, derivative of a constant is 0, and we'll put the neg 1 on a out front. Now, the derivative of cos is minus sine of ax plus b times by the derivative of the function inside there, the chain rule. There's our chain of derivatives. And then multiplying that, negative by negative is a positive. So it does work. Got to keep your wits about you going backwards and forwards here between the differentiation rules and the integration rules. So that's the subject of this presentation. That's all we're going to do, is to look at this simple application of composite functions, where the function inside, the g from fog, is actually a simple linear function. And of course, the last presentation you might like to guess is what? Want to guess? Okay, it's something like, let's say here, ax squared plus b to the n. Now, this poses a bit more of a problem, because the derivative of this function in here, the g function if you like, is not just a constant. The derivative of this function in here is 2ax. Now that poses some difficulties. I'm going to discuss that with you in the next presentation. So this one just deals with no power there. It's just a linear function. Okay, we have to treat that one specially. Let's go down and summarise now what we've done here. I've got two screen clippings here. This one is from the formula book that you'll be provided with in any exams and tests and so on. Okay, and there they are, just as we've found them before. We've had this before. That's what they give you. Now, this is the next level up from those functions. Remember what we're doing. We're trying to integrate, as we did with differentiation, more and more complex functions. So here, what we've just done, it's not e anymore, it's e to the ax plus b. It's not just x to the n, it's ax plus b to the n. So it's the next level up. These are composite functions. Fog of x, or gof of x if you like. F operated on another function. Here are our basic functions, f of x. And now we're coming down to composite functions, where we've got another little dude done first here. And that's, in this case, going to result in always dividing by the derivative of that linear composite function in there. Okay. Fairly easy to understand, I think. This is building up. We're building up into more and more complicated functions. Okay, so that we feel we can do our calculus, the integral calculus and the area and all that stuff, with some fairly sophisticated functions. All right, are you ready to have a look at some problems? Let's have a look now. And here's, again, screen clippings thanks to Hayes Publications here. We're going to work Pearson's work in towards the end, when we have done the last section on how to integrate functions. All right, let's have a look at the integral of 2x plus 3 to the fourth, naming the variable with respect to x, so the variable is x there. Okay, so what are we going to do? We increase the power by 1, divide by the new power, as if this was just an x. But then we have to divide by the derivative of that in there, because we are thinking this is a composite function. It would have produced a chain rule, so we've got to divide. We've got to reverse that multiplication by a derivative in the chain rule to dividing. And so we'll get 1/10 here. 5 by 2 is a tenth. 2x plus 3 to the fifth. Don't forget the plus c. There's a whole family of functions here which, when differentiated, would give this one. And they all differ just by a constant, because the derivative of a constant, as we looked at above there, is 0. What about this creature here? Well, it doesn't look to be the same, but it actually is. 1 on root 1 take 2x is 1 take 2x to the neg a half. negative because it's the reciprocal, 1 over, and a half because it is the square root. So what are we going to do? Increase the power by 1. This is doing the x to the n rule. Divide by the new power. We must also divide by the derivative of our g function. Okay, reversing the composite function rule, or the chain rule there, the functional function rule, we're reversing that. Don't forget to divide by that derivative. And so when we simplify it, of course, dividing by a half, you'll invert and multiply, and that's going to cancel out that 2 there. So we'll still have the negative, and the half power means it's a root, plus c. Okay. Do you get it? It's not hard, is it? Think about integration as anti-differentiation and you should be okay. But of course you've got to know the differentiation rules so you can reverse them. And then of course you can't get confused as which way you're going. So there are some traps here. Let's look at some work with E now. Okay, so integrating this function, let's do it. We leave the constant out the front. Now, integrating E, the integral of E is itself, e to the 2x. Then we have to divide by the derivative here, reversing differentiation, divide by that derivative. Minus, and then integrating E is itself. And then we have to divide by the derivative of that function. Because in the chain rule, remember, we will do the derivative of E and then multiply by the derivative of this function up here. So we're reversing that operation, we're dividing, plus c, and then we can simplify it. 2 times a half is either 2x, and then we've got negative by negative, positive, etc. You can go through that. What about this one over here? Let's write the problem down. Put the 4 out the front if you wish, or you can leave it in the front, just in here. 4 times. Now, integral of 1-ons, or reciprocals like that. The integral of 1 on x is ln of the thing, mod x. Here it will be mod of 1 take 2x, because this is a fog, isn't it? I hope you're not caught in the fog. Small joke. But here, yes, you've operated the reciprocal function, f, on the linear function 1 take 2x. So now we have to divide by the derivative of this function here. There it is, -2, 1 over -2. Okay, so then 4 times neg a half is -2 ln mod 1 take 2x plus c. Or you could leave it as a statement here without using the mod, where 1 take 2x is greater than 0. Just remembering what we're saying there, this is well and truly in the course, where we're talking about using the log function here. So you've got to say it only exists over there for positive x. So if you're trying to find the log of something, you have to consider its size being positive there, the absolute value or size of the number. So you use the modular sign or some statement about that. This goes back to domain and range work, doesn't it? From the first year of the course usually. All right, let's go on and do some more. Yep, you knew it. It's going to come up. It's cosine and sine. Okay, so we're going to integrate this. Another way of saying the problem might be if f dash x equals 2 sine 3x plus cos 4x plus pi, find f. Okay, that'd be another way of saying it. Find f of x. Okay, so this is what we're going to do. We're going to treat that as a derivative and we're going to integrate it. So let's look at this first function, leave the constant out the front, because you think of this as that many lots of the function, and so there will be that many lots of the integral. The integral of sine, remember sine is friendly under differentiation, derivative of sine is cos, on integration it's minus cos, and you leave the 3x there. But then you must divide by the derivative of this function, reversing the chain rule, so it's a third. Okay, and then over here, we're going to integrate cos. Cos is a problem under differentiation because the cos differentiates to minus sine. What's the negative? Well, coming backwards, then the integral of cos is just plus sine, so that's friendly. Sine of 4x plus pi, and then you've got to divide by the derivative of what's in here. The derivative of pi is nothing, of course, but the derivative of 4x is 4. So then we have, putting it all together, we have our answer here. And not forgetting on the first line, on the very first line, when you integrate, you must include the c. Okay, remembering there's a whole family of functions, all differing by just a constant, which when differentiated would take you back up there. Okay, are you getting it? You've got to keep your wits about you. Which way are you going? Don't get confused. You will have the formula book to help you. And so what I tell students is when you're practicing, have that formula book handy by so that you get used to it and know what's available to you. But let's integrate this one now. 2 take sine x all squared. Using this identity here. Sine squared is a half take a half cos 2x. Where did that come from? Well, if you check the formula book, it comes from the section where you have the double angle formula. Cos 2x is cos squared x take sine squared x, or it's what can we have? 1 take 2 sine squared x, or 2 cos squared x take 1. And what they're saying here is if you use this one and rearrange it, you get cos 2x take 1 equals neg 2 sine squared x. Dividing both sides by 2, you get, what have we got here? No, neg 2, sorry. So it's neg a half cos 2x plus a half equals sine squared x. Or better said, a half take a half cos 2x equals sine squared x. So it's scribbly in there. Okay, so it's a rearrangement of this one. And it can be handy. Let's see why. Let's come over here now and say if we expanded that, you'd have first one squared twice the product would be neg 2 sine x, so twice it would be neg 4 sine x plus sine squared x. Okay, so now we can't actually do this one very easily. You might say, well, why don't you increase the power by 1 and divide by the new power? Yes, but then we should also, from the chain rule, divide by the derivative of sine, which is cos. We've got a problem here, because if we check that back and reversed it, would we use the chain rule on this? No, we wouldn't. There's a contradiction here. To reverse that, we would use the quotient rule. So we have a contradiction. So if you're reversing, and that is anti-differentiation, a function, the derivative of this one in here cannot be itself a function in x. That's what we talked about earlier, where you can divide by the a from ax plus b, but not if it contains an x, that derivative. And we're going to come and look at that in the final presentation on how to integrate. So what will we do here to avoid that? Because this won't work. Can't reverse the chain rule on the sine squared there. So we're going to put a half take a half cos 2x, because then there isn't a problem of a function of a non-linear function in x. Okay, if you don't worry about that too much at the moment, we'll come back and have a look at it. Let's have a look now at the integral. Now, so let's tidy some of this up. We've got 4 plus a half, 4 and a half. Take 4 sine x, take a half cos 2x. Let's do it now. Now remember, the derivative of a constant is 0, but the integral is that many x's, 9 over 2x, and the constant stays there, and the integral of sine, remember sine is friendly under differentiation, but it's got a negative for integration, so that becomes negative cos x was plus 4 cos x, constant stays out the front, integral of cos is friendly, it's sine of the same thing, but then we must divide by our derivative of that function in there, which is linear, so derivative is constant, it's a half. So we're doing the same thing. As soon as we do it, we must add the c, and then we can tidy up down here, half by a half, and is a quarter. Okay, lots of thinking to go on there. All right, now it's your turn, and I've got some problems here again from Hayes Publications of their third edition of the standard level textbook here. So I suggest you do quite a few of these, and the answers are down below as before, and so you can scroll through and look at them after you've had a go. Alright, so I think it's all a matter of just going carefully. Do not forget the C. Very important concept there. When you integrate it, it is not just a single function that would give you that derivative, so you must put that in. Okay, watch for these little fellows here. dy by dx. All simply means I want y back again, I've got the derivative. To get the function back, I integrate. And you'll be able to evaluate your C, won't you? Because you're given those conditions, as we saw before. So watch these little tricky ones. You might have to set up some equations here. Not just a derivative, but you'll also know it goes through that point on the original function. So have a look at that. Alright, let's go down. Using the identities help you integrate this. Well, there's the other one, the rearrangement of the 2 cos squared x take 1 in the cos 2x identities. So you can play with those. There's question 4 and 5. A little bit of E work in 6. 6 and 7. Just remembering, if you have a derivative and you want to go back to y, that's called integration, anti-differentiation if you like. Okay, here's a couple of good problems coming up down here. We'll put all of them up, I think, now. Can we get them all on? Yeah, we can get them all on. So this is an interesting problem. Be careful with this one. Okay, question 8. And question 9 is interesting too. Have to work with p's. The IB rather like this sort of statement, find p and q such that some conditions are upheld. But you might try to check this with differentiation, these two, and then explain what's going on there. Okay, interesting question 8. Good to discuss with classmates and teachers and things about that one. Okay, what do we got here? Consider a function here with sine. Yep, this isn't too bad. Just look at this little variation here. And then you go on. And of course, when you're given a condition like this, that enables you to evaluate C and come to a specific member of the family. Okay. All right, have a look, see what you can do. Information here. That's all pretty good, I think. And this is a good identity one here. So that instead of integrating that all squared, you can integrate its equivalent. So there's a good link up. What's the word hence? It says you should use what came before, and so you will change this function to the integral of that and just set it out. Make sure you follow the command terms here. Hence, it says you have to use not what's given there, but something from before. Okay. All right, I'll leave you with those. I'll go down and show you the solutions now. All right, question 1 to 4, a bit of 5 there. Let's go through to 11 and 12. Oh, there they all are now. Okay, so that's got the whole lot of them. All right, so it's an area where you've got to keep your wits about you. It isn't conceptually hard. We're going forwards and then we're going backwards. It is a little bit difficult to remember, I think, which way you're going. That's important. Okay.